you're just rotating. Just be 2 pi n over 2, isn't it? Something. Right. So you're just rotating pi radians, 180 degrees. And so if you do that twice, you just get back to the unit. That's a group, subgroup, and it's order 2. If the number of sides is even. So that would give you an extra subgroup of order 2. So if the number of sides is n is odd, then the answer is n. This type. But if the number of sides is even, you'll have these n plus this one, where you're rotating, where your A is a rotation of 180 degrees. Yeah. Right. Now, here, the point of this question, that was question 5, is you're basically trying to show that each element in your dihedral group, they're all distinct. Well, it has to be, right? But how to actually prove that? Now, I've rubbed it off, perhaps I should have left it. But remember your dihedral group, the members are E, A squared, A cubed, dot, 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 A to, so here, E, A squared, dot, 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 A to the n minus 1, and then B, BA squared, dot, 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 B to A n minus 1. Right? They're the members of your dihedral group, Dn, general. And they're all distinct, and you have to prove that. How to show that? So that's the point of this question. So it's asking if two members, for different I and j, like, I don't know, say that one or this one, any two of these, B A of some, where the A is to some power, I or j. If these two are equal, show that these, so effectively they're the same element. So in other words, each, if the i's and j's are different, then this cannot be equal to that. So they're distinct, which is the point of the question. Right, so if BAI equals BJ, and perhaps I should first say, all these ones are obviously different. Why is that? Because you're rotating about different angles. Right? Like A squared would be rotating about an angle twice what A is, and A cubed would be rotating at 3 times that angle, and so on. So each of these A's here are distinct. They're different because you're rotating about a different number of degrees, right? Okay, so if we assume any two of these have the same value, you're assuming here, then show that I equals j, right? Well, let's assume that BAI equals BJ, AAIJ. Now, this is just a member of a group. It's an element of a group. It has an inverse. So pre-multiply both sides by B inverse. So you'll get AI equals AJ. And that means that AI minus J is E. Okay? And that can only happen if I minus J is naught. Right? A raised to what power gives you the unit in this context? Well, it'll be 0. So I minus J is 0. So I equals J. So I equals J, which is what you're asked to do here. All right, and you're also asked to show that these ones are distinct from these. Right? We've just by showing this, we've shown that amongst the B's, amongst the hedral type operations, they're all distinct. These are all distinct. okay? Because they're different, rotating about different angles. So now we need to show that any one of these is not one of these. And if we can do that, then they're all distinct. Okay? So let's assume, let's do it by a contradiction, proof by contradiction. So let b to the ai be equal to one of these, to let's say aj. So bai, let it be equal to say aj. Right? So post multiply both sides by a to the minus j. So you'll get bai minus j equals e. So that makes sense. No, I'll go the other way. That's not so smart. I'll go the other way. Post multiply by a to the minus I. Post multiply by a to the minus I. So that'll give you b, and on the right hand side you'll have a to the j minus I. Right? Now, so that means b is just some power of a. Now that's impossible, because what is b? b is one of your flip operations. Right? And a, that's just some kind of rotation on one face, in the plane. It'll just rotate you this way. But b, whatever it is, it's a flipper. Right? So there's no way you can rotate by different a's and get something that's flipped. No way. So b cannot be of the form of a to some power. Right? So therefore you've got a contradiction, and therefore this assumption is false. You go back and you negate what you negated to start with. So not gives you what you're trying to prove. Right? So that gives you that. All right. So that's done. So that's the end of this lecture. And the next one, which will be lecture 14, so getting towards the end of the course, lecture 14 is about something called cosets, and I'll explain what that is very early on next lecture. And the concept of a coset is needed to understand, to prove Lagrange's famous theorem. And once we have Lagrange's theorem under our belt, we can really start analysing the structure of groups. What kinds of subgroups do they have? And you can start asking questions like, if someone just gives you an integer and asks the question, what kinds of groups have that order, equal to that integer? So it's like, how many different kinds of groups can you have for a given integer, meaning a given order of the group? Now, in earlier lectures we were asking, how do you distinguish between two groups that have the same order but different group tables? They're not isomorphic, right? So that implicit in that analysis was that for the same order, the same size of the group, you can have different groups, right? Because their tables are different. They are not isomorphic. So that in turn might motivate you to ask the question, well, for a given order, how many different types of groups are there? Right? So you're now beginning to classify groups of a given order. So in 2 lectures from now, we will analyse, we'll answer the question for order up to 8. So how many different types of groups are there? How many different types of groups are there of order 2? of order 3, of order 4, 5, 6, 7, 8. Now immediately we can throw out all the all the prime numbered orders. So for 2, 3, 5, 7, they're all prime numbers, and that means they have no subgroups, right? And that simplifies the analysis a lot. So then the analysis focuses on, well, how many groups could you have of order 4? Or order, in fact, the even, where the order is even and non-prime. So 4 and 6 and 8, that kind of thing. So it gets more interesting. So that's like 2 lectures from now. So I'll stop there and see you now. The next lecture on cosets and Lagrange's theorem. Quite a bit of theory, right? A lot of theory. So if you like theory, next lecture should please you. So ciao.